The product rule, level 1. In the previous videos, we learned that the derivative of a sum and/or difference of functions was equal to the sum and/or difference of the derivative of the individual functions. The next question we should ask is if this pattern also works for the product of two functions. In other words, is the derivative of a product of two functions equal to the product of the derivatives of the functions? Let's test this out with the following functions. Let f of x equal x cubed and g of x equal x raised to the power of 6. The product of these two functions is equal to x raised to the power of 9, and the derivative of this function is equal to 9x raised to the power of 8. Now let's verify the right side of this expression. So we go ahead and take the derivative of f of x and g of x as follows. Now, if we were to multiply them, we should obtain 9x raised to the power of 8. But, unfortunately, we obtained something completely different, in this case, 18x raised to the power of 7. This means that this expression does not hold. In other words, the derivative of a product is not the product of the derivatives. It turns out that in order to find the derivative of functions formed by multiplication, we have to make use of the product rule. The product rule says that the derivative of a product of two functions is the first function times the derivative of the second function, plus the second function times the derivative of the first function. In prime notation, the product rule can be written as the derivative of f times g equals f times g prime plus g times f prime. Remember, the functions f and g have to be differentiable. Also notice that it really does not matter which function you assign as your f of x and which one you assign as your g of x. As long as you're consistent with your choices, everything will work out. We can also rewrite the product rule as follows. F prime of x times g of x plus f of x times g prime of x. Some students prefer this version because it generalizes easily to products of 3 or more functions. For instance, the product rule can be extended to cover products involving more than 2 functions. For example, if f, g, and h are differentiable functions of x, the derivative will be equal to f prime of x times g of x times h of x plus f of x times g prime of x times h of x plus f of x times g of x times h prime of x. Notice that the derivative, or prime symbol, alternates between the functions. This only works if you keep the order of the functions consistent. Keep in mind that the derivative of a product of two functions is not, in general, given by the product of the derivatives. Alright, with that said, let's see the product rule in action and go over some examples. Find the derivative of r of x equals x cubed times e to the x. The first thing you should notice is that we have a product of two functions. In this case, we have the power function x cubed and the exponential function. Since we have a product of two functions, we can find the derivative by making use of the product rule. In order to apply the product rule, we need to decide which function is going to be the first function, in this case f of x, and which one will be the second function, in this case g of x. Keep in mind that it really does not matter which function you assign as your f of x, and which function you assign as your g of x. It is totally up to you. Just make sure you apply the product rule correctly once you made your decision. For this example, I will assign x cubed as f of x and e to the x as g of x. With this assignment, we go ahead and apply the product rule. So we take f of x, or first function, and multiply it by the derivative of g of x, the second function. Then we add the product of g of x and the derivative of f of x. Simplifying the expression, we obtain the final derivative equal to x cubed times e to the x plus 3 times e to the x times x squared. We can also rewrite this expression by factoring out an x squared times e to the x term. In any case, both forms are acceptable expressions for the derivative. Alright, let's try the next example. Find the derivative of r of x equals e to the x over the square root of x. Notice that in this example, we have a quotient of two functions. At first glance, it seems that we cannot use the product rule to find the derivative of this function. It turns out that we can actually apply the product rule to this function. All we need to do is to rewrite the expression into a product rule friendly form. In order to accomplish this, we can rewrite the radical in the denominator as x raised to the power of negative 1/2, as follows. Now we can go ahead and apply the product rule. I will assign e to the power of x as my f of x, the first function, and assign x raised to the power of negative 1/2 as my g of x, the second function. Remember, it really does not matter which function you assign as your f of x and g of x. As long as you're consistent with the product rule, everything will work out. Applying the product rule, we obtain the following expression. The first function times the derivative of the second function plus the second function times the derivative of the first function. Simplifying and rewriting the expression, we obtain the following for the derivative. E to the x over the square root of x minus e to the x over 2 times the square root of x cubed. Keep in mind that you might need to rewrite an expression so that you can apply a specific differentiation rule. Alright, let's try a slightly more challenging example. Find the derivative of r of x equals e to the x times the quantity x squared minus 2x. Here we have a product of two functions, so let's go ahead and use the product rule. Let's assign e to the x as our f of x, and assign the quantity x squared minus 2x as our g of x. Next, we find the derivative by applying the product rule. So we take the first function and multiply it by the derivative of the second function, and add the second function and multiply it by the derivative of the first function. Notice that in order to take the derivative of g of x, we need to apply the sum rule and power rule. Having applied the product rule, we go ahead and simplify the expression. Here we can factor out an e to the x term. This leaves us with the following. Then, it is just a matter of simplifying the expression inside the brackets. Doing that yields the final derivative equal to e to the x times the quantity x squared minus 2. Okay, now let's try finding the derivative of a product of polynomials. Find the derivative of p of x equals the quantity x plus 3 times the quantity x squared minus 5x plus 2. I hope you recognize this function. This was the last function we worked on from the previous video. We can actually find the derivative of this function by using the product rule. Let's go ahead and assign the binomial as our f of x and the trinomial as our g of x. Next, we go ahead and apply the product rule. So we take the first function and multiply it by the derivative of the second function, and add the second function times the derivative of the first function. Next, we go ahead and FOIL the expression on the left. Then we go ahead and simplify the expression by combining like terms. Doing that yields the final answer equal to 3x squared minus 4x minus 13. This is the same answer that we got in the previous video. Notice that we could also find the derivative of this function by distributing the binomial and then taking the derivative of each term, like we did in the previous video. Either method would generate the same expression. Alright, let's try the final example. Find the derivative of p of x equals the quantity x cubed minus x times the quantity x squared plus 2 times the quantity x squared plus x minus 1. Notice that we have three functions being multiplied. One way we can find the derivative is to apply the product rule by assigning the product of two functions as our f of x, and assign the third function as our g of x. Then you would just carry out the product rule with these assignments. Taking this approach would force you to apply an additional product rule when trying to find the derivative of f of x. There's really nothing wrong with finding the derivative in this way. I actually encourage you to find the derivative in this manner, so you can practice applying the product rule multiple times. We can also find the derivative by using the product rule extended for more than two functions. In this case, we would need to assign three functions as our f of x, g of x, and h of x. For this problem, we will assign f of x to be the first binomial, g of x the second binomial, and the trinomial as our h of x. Then, it is just a matter of writing all the functions, making sure that we alternate the derivative to each distinct function as follows. Doing that, we obtain the following derivative of the expression. Technically, we are done. This crazy looking polynomial is our derivative. If you like, you can go ahead and simplify the expression by distributing and collecting like terms. But there is really no need to do that. If for some reason you want to simplify because you want to practice your distribution and collecting like term skills, the resulting polynomial you should obtain is as follows. 7x raised to the power of 6 plus 6 times x raised to the power of 5 plus 4x raised to the power of 3 minus 9x squared minus 4x plus 2. Note that you can also just distribute the expressions in the beginning and then apply the derivative term by term. That would also yield the correct answer. But for expressions that are not polynomials, you want to use the product rule extended for more than two functions. Alright, and that is the product rule in a nutshell. In our next video, we will go over more challenging examples involving the product rule. The product rule, level 2. In this video, we will go over more challenging examples that require the use of the product rule. The following examples require you to really understand the product rule and combine it with various algebra and calculus concepts learned so far. The first type of problems involves writing an expression for the derivative in terms of the given functions. Let's take a look at the first example. If p of x and q of x are differentiable functions, find an expression for the derivative of the following function. R of x equals p of x times q of x. Notice that in this example, we're given the function r of x, which is written in terms of two other functions, in this case, p of x and q of x. The problem is asking us to find the derivative of this function. At first glance, it might be a little weird that we are asked to find the derivative of r of x, written in this manner. It does not seem to contain any constants, power functions, or natural exponential functions. All we know is that r of x is defined by the product of p of x and q of x. This means that we need to somehow work with these expressions and find the derivative. Since r of x is defined by a product of two functions, it is natural to apply the product rule to find the derivative of r of x. So we will assign p of x as a first function and q of x as a second function. With these assignments, we go ahead and apply the product rule. The derivative of r of x is going to be equal to p of x times q prime of x plus q of x times p prime of x. And this is the final derivative. At first, it might be hard to wrap your head around this. If we knew what p of x and q of x was equal to, we would still find the derivative in this manner. All we are doing here is finding an expression for the derivative of r of x, which was defined by two distinct functions, p of x and q of x. If we knew what p of x and q of x were equal to, then we would just substitute them into our expression. In this case, we just want a general expression for the derivative. Let's try another example. If p of x and q of x are differentiable functions, find an expression for the derivative of the following function. R of x equals x squared times q of x plus p of x. Alright, notice that we now have a function r of x defined by a power function along with the functions q of x and p of x. Similar to the previous example, we are asked to find an expression for the derivative. So we go ahead and take the derivative of this function term by term. For the first term, we have a product of two functions, in this case, x squared and q of x. Since we have a product of two functions, we need to apply the product rule. we're going to assign x squared as the first function and q of x as the second function. Applying the product rule, we obtain x squared times q prime of x plus q of x times 2x. Next, we move along to the second term. The derivative of the second term is just going to be equal to p prime of x. Rearranging the expressions, we obtain the final derivative equal to x squared times q prime of x plus 2x times q of x plus p prime of x. Once again, this expression represents the derivative of r of x in terms of q of x and p of x. If we knew what p of x and q of x were equal to, we would just substitute them directly into this expression. Alright, let's try one more example. If p of x and q of x are differentiable functions, find an expression for the derivative of the following function. R of x equals q of x over x plus e to the x times p of x plus 5x. Similar to the previous examples, let's go ahead and find the derivative of this expression. This function is defined by three distinct terms. The first term contains the function q of x and the rational function 1 over x. In order to find the derivative of this term, we need to rewrite it into a derivative-friendly form. In this case, we can rewrite it as q of x times x raised to the power of negative 1. Now we can go ahead and apply the product rule with q of x as a first function and x raised to the power of negative 1 as a second function. Applying the product rule, we obtain the following expression. Next, we move along and find the derivative of the second term. Here, we also have a product of two functions. In this case, the natural exponential function times p of x. So we go ahead and apply the product rule with e to the x as our first function and p of x as our second function. Applying the product rule, we obtain the following expression. Lastly, we find the derivative of 5x, which is just equal to 5. Simplifying and rearranging the terms, we obtain the final expression for the derivative, which is equal to negative q of x over x squared plus q prime of x over x plus e to the x times p prime of x plus e to the x times p of x plus 5. Alright, now let's try a completely different type of problem. Suppose g of 2 equals 3, g prime of 2 equals negative 2, h of 2 equals negative 1, and h prime of 2 equals 4. Use this information to find f prime of 2, where f of x equals g of x times h of x. Notice that we are given values for the functions g and h, and their respective derivatives, evaluated at x equals 2. Also, we are given that f of x is equal to the product of g of x and h of x. This problem is asking us to find the derivative of f evaluated at x equals 2. Note that some textbooks might ask you this question by using the following equivalent forms. The derivative of g times h evaluated at x equals 2. Both expressions denote the fact that we are looking for the derivative of g of x times h of x evaluated at x equals 2. Alright, at first, this problem might seem confusing, but the idea is to first find the derivative of f of x. Once we have an expression for the derivative in terms of g of x, g prime of x, h of x, and h prime of x, we go ahead and evaluate the derivative at x equals 2 using the information that is provided to us. So let's go ahead and first find the derivative of f of x. Since this function is formed by a product of two other functions, we make use of the product rule. F prime of x is going to be equal to g of x times h prime of x plus h of x times g prime of x. Having found the derivative, we go ahead and evaluate the derivative at x equals 2 as follows. The next step is to replace the values of g of 2 and g prime of 2 with 3 and negative 2 respectively, and replace h prime of 2 and h of 2 with 4 and negative 1 respectively. Then, it is just a matter of simplifying the expression. Doing this, we obtain the final answer equal to 14. These types of problems requires you to first find the derivative of the function in terms of the given functions, then use the information that is provided to evaluate the derivative at a given value of x. Let's try another example. If f of x equals e to the x times h of x, where h of 0 equals 5 and h prime of 0 equals 2, find f prime of 0. Alright, here we need to find the derivative of f evaluated at x equals 0. Notice that this function is formed by the product of the natural exponential function and h of x. Similar to the previous example, let's first find an expression for the derivative of f of x. Applying the product rule, we obtain e to the x times h prime of x plus h of x times e to the x. Remember, the derivative of the natural exponential function is just equal to itself. Now let's find the derivative of f evaluated at x equals 0. Notice that we have values for both h of 0 and h prime of 0. So we go ahead and substitute those values into our expression. We also want to evaluate the natural exponential function at x equals 0. Doing that, we obtain the following. The final step is to simplify the numerical expression, obtaining 7 as our final answer. These types of problems might seem a little intimidating at first, but as long as you understand that we're just looking for the derivative in terms of other functions, then the entire problem just becomes a standard find the derivative problem. The only difference is that you're given values of the function at given values of x. Alright, in our next video, we will go over problems that require us to use graphs to find the derivative of a given function. The product rule, level 3. In this video, we will go over problems that require us to use the graphs to find the derivative of the given function. Let's go over the first example. Let p of x equal f of x times g of x. Find p prime of 1 by using the graphs of f and g. Alright, this example is similar to the problems from the previous videos. We're given a function that is formed by the product of two distinct functions, in this case f of x and g of x. We also don't have an analytical expression for the function, but we are provided with the graphs of these two functions. For this problem, we are asked to find the derivative of p evaluated at x equals 1. Let's first find an expression for the derivative of p of x. Since p of x is formed by the product of f of x and g of x, we go ahead and apply the product rule. Applying the product rule, we obtain the following expression for the derivative. Next, we need to evaluate this expression at x equals 1. This means that we need to find the value of f of 1, f prime of 1, g of 1, and g prime of 1. Unfortunately, these values are not provided to us, like they were in the previous video. This time around, we need to figure out these values by making use of the graph of f of x and g of x. To find f of 1, we go ahead and find the y-coordinate of the red graph when x equals 1. Looking at the graph, we see that it would be equal to 6. In the same manner, the y-coordinate of the blue graph at x equals 1 would be equal to 4. This would correspond to the value of g of 1. Now to find g prime and f prime evaluated at x equals 1, we need to remember the geometric interpretation of the derivative. In this case, the derivative represents the slope of the tangent line at every given value of x of the function. This means that in order to evaluate g prime at x equals 1, we need to calculate the slope of the tangent line of g of x at x equals 1. Since the blue graph at x equals 1 is formed by a line, we can find the slope by calculating the rise over the run. In this case, it is going to be equal to -1/2. Lastly, f prime evaluated at x equals 1 is going to be equal to the slope of the tangent line of the red graph at x equals 1. This value can be calculated in the same manner as g prime of 1. In this case, it is going to be equal to 1 over 1, which is just equal to 1. Having found all the required values, we go ahead and simplify the expression, obtaining the final answer equal to 1. This problem is testing a couple of things. First, it is testing to see if you understand the product rule. Second, it is testing to see if you understand what g of 1 and f of 1 represents. In this case, they are just the y-coordinates on the respective graph at x equals 1. Lastly, do you know how to find g and f prime by using the geometric definition of the derivative? Remember, it is just the slope of the tangent line at any given point on the function. Alright, let's try the final example. Let p of x equal f of x times g of x. Find p prime of 4 by using the graphs of f and g. Similar to the last example, let's go ahead and find an expression for p prime of x. From the previous example, we know that it is going to be equal to the following expression after using the product rule. Next, let's go ahead and find p prime evaluated at x equals 4. We first need to find what f of 4 is equal to. Looking at the red graph, we see that the y-coordinate of this curve at x equals 4 is equal to 1. Likewise, g of 4 can be found by using the blue graph. In this case, it will be equal to 8. Next, let's go ahead and find g prime and f prime evaluated at x equals 4. Once again, in order to find the value of these expressions, we need to calculate the slope of the tangent line at x equals 4 for each graph. G prime of 4 is going to be equal to 0, since the slope of the tangent line at this point is a horizontal line with no slope, or in this case, 0 slope. Lastly, f prime of 4 is going to be equal to positive 1/2. Substituting these values into the derivative and simplifying the expression, we obtain the final answer equal to 4. Keep in mind that whenever you need to find the derivative of a function formed by products of functions, you need to make use of the product rule. In our next video, we will learn how to deal with functions formed by a quotient of two distinct functions.